So this is a joint work with Dmitry Kurzke, Alberto, Montero, and Spirn. I am going to talk a bit about motivation, what led us to consider these type of problems. So then I will discuss the main topic, which is cross fields and frame fields that are defined by higher order tensors. Then I'll show some numerical pictures so that you have a better understanding of how these fields behave. And then at the end, I'm going to talk about the tetrahedral frame fields. So our original motivation to consider this, besides the fact that all of us have worked in areas close to the Ginzburg-Landau, and this, as you will see, also ends up sort of as a generalization of a Ginzburg-Landau theory. So the original motivation was a Ginzburg-Landau-type problem that arises in the question of meshing. So a brief introduction into this. So typically there are two main types of meshes that people consider in 2 dimensions: triangular mesh and quad mesh. Triangular on the left, quad on the right. Triangular is typically much easier to produce because it's local. For example, in this case, say if you just add one more point here, then you can modify the mesh by simply introducing 3 additional edges. You don't need to modify things away from this point. On the other hand, for quadrilateral mesh, introducing an additional point is going to induce global changes. But on the other hand, so the quadrilateral mesh is more difficult to produce, but it is less desirable for a variety of reasons that I'm not going to discuss. So you want to produce quadrilateral mesh, but it's easy to produce a triangular mesh. So one way to develop quadrilateral mesh is to use a paving algorithm similar to what you see here. For some strange reason borrowed from a paper, and for a strange reason it goes from bottom to top and from left to right. So you start with a domain like this. The domain with holes, you try to pave, and there are obvious issues that are going to arise when paving from different directions are going to join together. So what you want to do is to generate a quadrilateral mesh, which is of high quality. So this is obviously better quality than this one. And a mesh that adheres to the boundary well. There is an obvious problem, right, that in this case, if the mesh is, for example, orthogonal to the boundary, then for topological reasons, then you would develop defects, and you want to have as few of those as possible. And so one mesh generation process consists of the following steps. You generate a triangular mesh first, then you solve a variational problem to generate a cross field. So the cross field, basically at every point in the domain, with every point you associate in 2D just 2 orthogonal lines. So you generate this cross field in some prescribed way. And then you can follow streamlines along the crosses to generate a quadrilateral mesh. So this is one illustration of this process in 3D. So In this case, actually, this picture was developed by using the algorithm that I'm going to describe later on. So we found a cross field in this case, which is, in this case, a cross field. It's actually a frame field. It involves 3 orthogonal lines at every point, an orthonormal frame at every point. So you generate orthonormal frame field in this domain, and then you can generate the streamlines and follow the streamlines to get the mesh. Okay. Now, this problem of generating quadrilateral mesh, in a sense, it resembles of the process of trying to, for example, to have a crystalline solid. In this case, maybe having a square lattice with lattice vectors being perpendicular to the boundary. So you can imagine that a configuration like this, theoretically it might be possible. This configuration, again, for topological reasons, will have 4 disclinations. So that means that, in a sense, the process of filling out a space or a 3-dimensional domain with an orthonormal frame field or a 2-dimensional domain with a cross field, in a sense, is sort of analogous with trying to fit into such a domain an orthogonal or a square, orthonormal or a square lattice. So this is something that an algorithm, version of algorithm that was proposed by people who do meshing. So what they proposed in 2 dimensions was to basically solve a Ginzburg-Landau-type problem. Define a vector u like this. It is going to have attached to the boundary in such a way so that the vector cosine theta, sine theta, let's say, is normal to the boundary. Then for u, the phase spins 4 times faster than theta. And so in that way, by minimizing this, minimizing the Ginzburg-Landau functional for nz's like this, basically, you minimizing it in a class of functions with degree 4, and you are able to produce a cross field, so a field of lines, as I described previously. And so in 2D, this process is sort of easy because it's essentially you have to solve a Ginzburg-Landau problem, except that you're identifying rotations by each rotation by 90 degrees, right? That you're symmetric with respect to these rotations. So really, it's the same process as the Ginzburg-Landau. In 3D, things are not so easy, not so obvious. And so when we thought about it, we thought that it would be, in order to answer the question, it is a good idea to think about what is going to happen for Q tensors in a theory for nematic liquid crystals, something that has been already discussed here a few times. So I'm just going to go through this very quickly. In this case, if you have a nematic liquid crystal, it consists of molecules that have a preferred orientation. Head and tail of the molecules are equiprobable. So if you want to describe in some way the probability distribution of molecules at every point, you instead consider the moment. Because the probability of finding the molecules pointing in opposite directions is the same. So when you consider moments, the first moment is obviously 0. So the first significant moment is going to be the second moment. And that is Q tensor. Typically, you subtract 1/3 of the identity from this second moment just to turn it into 0 in the isotropic state. So inspired by this, we started thinking, we want to fill the three-dimensional space with these orthonormal frames. So with every point, we want to identify a set of 3 orthogonal lines. Because these are lines, then it's not really 3 vectors, but that we want to identify with every point, but 3 projection matrices. So we have 3 orthonormal vectors, ai and j, or denoted here by aj. What I'm talking about is not necessarily applicable to R3, so it's in Rn. So if you have a set of n vectors in Rn, if you want to define a frame which consists of n vectors, of n orthogonal vectors, of n orthogonal lines, then you define n projections. And then what you want this object that you're talking about, you want it to be symmetric with respect to all possible rotations by 90 degrees. So an obvious thing to consider then is to just add all of these projections. But unfortunately, this is going to give you a constant vector, constant tensor, constant matrix. So you get no information from this object. So you need to consider higher order tensors. And so the third order tensor is not going to work again because of symmetries, because of inversion symmetry. So the next order is a fourth order one. And indeed, then in this case, it turns out that this is the first non-trivial tensor that you can construct out of these n vectors. And so that is going to be the object that I'm going to talk about in the first part of my talk. Now, in addition to the fourth order tensor, we can think about its blocks or submatrices defined like this. So Qij simply is defined in this way. And also, fourth order tensor in Rn will have n to the 4th elements. So you can also associate it with the matrix with the size n squared by n squared. So the matrix or the tensor that you get in this case is symmetric because it should be invariant with respect to permutation of n vectors out of which this tensor is constructed. You can verify that this tensor will satisfy the condition that it is a projection. So if you square it, it is going to coincide with the tensor itself. And because the vectors out of which you constructed the tensor are orthonormal, then each block of the fourth order tensor is going to be either trace free or have a trace 1.
Sorry, what do you mean by squaring a fourth order tensor?
So think about it as you reshuffle the elements to have n squared by n squared matrix, and then just take a product of 2 matrices. That's, so for symmetric tensors, this would be the same thing as, for example, multiplying 2 tensors, taking a tensor product and contracting along 2 indices.
But in that sense, it's less universal, right? Because you have to decide on a pairing of these 4 entries.
Well, in this case, all of these pairings end up working in the same way. Because of asymmetry. Because of asymmetry, because of this item number 1, because of the permutation invariance. All right. So now that means that we're going to have one nonlinear constraint. So these tensors, fourth order tensors that we're talking about, really satisfy one nonlinear constraint here. Linear constraint asymmetry, linear trace constraints. And then if you start counting the number of elements, then for example in 3D, then you'll have 9 independent entries for something like this. Additional property that one can verify is that the submatrices or blocks of this fourth-order tensor, in this particular case, if you construct it out of the orthonormal frames, commute. And because they commute, then in fact, in this case, for example, we can extract an eigenframe. So each orthonormal vectors, in this case, vectors of a frame, are eigenvectors of these blocks, and so each block then shares the same eigenvectors. Then you can recover the original vectors of the orthonormal frame simply by computing eigenvectors of individual blocks. And conversely, so now if one has a fourth-order tensor which satisfies the conditions that it is symmetric, satisfies the trace conditions, and it satisfies a nonlinear constraint, if you can show that in this case the blocks are going to commute, then you get a recovery procedure. So if you have a Q tensor, you should be able, if you have this fourth-order Q tensor, you should be able to recover a frame, orthonormal frame from it. This, by the way, is not really obvious at all. So the fact that the blocks commute eventually is going to be a consequence of the nonlinear constraint that Q squared is equal to Q. So just to summarize what I'm going to do, so I'm going to consider a set of symmetric rank K tensors in Rn, satisfying the trace conditions. So we take a set like that. I'm not going to initially impose a condition that these tensors satisfies a nonlinear constraint. And we're going to work with these tensors, so I want to discover two things. So number one, recovery, that if I impose a nonlinear constraint, then I should be able to recover the vectors of the frame from the tensor itself. And number two, instead of imposing the constraint per se, just imposing it, I can relax a constraint and do the usual thing, penalize a constraint, and with some large parameter, let this parameter go to infinity, and see if I will be able to recover the frame in this way. Let's see. So this is what I just said. So one more thing. So now let's say that we have a two-dimensional or three-dimensional domain, and I want to fill this domain with the orthonormal frame. Because of topological constraints, I will not be able to do so. Right? I will not be able to find the smooth field that will fill the domain. So then instead, what I can try to do is to do a Ginzburg-Landau-type relaxation. So look at the tensors which do not satisfy the nonlinear constraint. And okay, let me skip that for a moment. Sorry. Okay, let me just say that. So I'm going to look at the tensors that do not satisfy the linear constraint. They're symmetric and satisfy the trace conditions. And I want to solve the Ginzburg-Landau problem for these tensors. So, like I said, we can do, I'm not sure in which direction I'm going. Okay, so as I said, we can do recovery. So by imposing the nonlinear constraint. I will skip the details of that. We can impose boundary conditions. So boundary conditions in this case have to be imposed on for the tensors. You can do this in two ways. Now, the boundary conditions that I'm interested in are basically that I want to, remember that I said that for mesh, I want mesh to be attached to the boundary in a perpendicular way. So from a point of view of the tensor, it just means that the normal to the boundary wants to be one of the vectors in the frame. So that condition can be imposed in two different ways, either strongly or weakly. Strongly, that means that you impose a constraint on the boundary, or weakly, you have a standard for people who are familiar with weak conditions imposed in the theory of nematic liquid crystals. This is a similar condition. So, write any popular condition that is something similar to it, except for higher order tensors. Now, when you do this in 3D, for example, so you have a normal vector, which is a part of the frame, orthonormal frame. The orthonormal frame consists of three vectors. So if one vector is perpendicular to the boundary, and let's think about the ball in this case, the other two vectors are parallel to the boundary. And so then, by Hady-Ball theorem, then you would expect that your field in the plane of the boundary is going to develop singularities for orthonormal frame in 3D. For orthonormal frame in 3D, that means if you think about it, there has to be 8 degree 1/4 singularities on the boundary, so on the surface of the boundary. Again, I'm going in the wrong direction. Okay, so we have two possible problems. The Ginzburg-Landau-type problem, so gradient of Q squared in this case is simply we want to penalize variations of your full-order tensor throughout the domain. We have a nonlinear constraint Q squared equal to Q penalized in this way. And we have, just like I said, two choices. One choice, the vector field satisfies Q-stride boundary conditions, or we have a surface energy added to this surface energy of this form. Okay, so then for the pictures that I'm going to show you, what we did, we just in the beginning we tried to understand exactly what the structure of the minimizers or local minimizers or stationary points for this energy functional would be. So what we did is we tried to run a gradient flow for this energy. Now recall that in this case we have 9 independent components for the tensor Q when this tensor belongs to the manifold of frames. Now we relax the condition because if I don't impose nonlinear constraint, there are actually more independent variables. I think there are 15 if I'm not mistaken. And so you run the gradient flow, which you can write in this form. So for these, you can just simply write a vector Q consisting of these independent components of a tensor. So you run the gradient flow. I will skip that. And so this is an example of what you're going to get in 2D. So some pictures that I'm going to show are in 2D, some in 3D. So in this case, it's 2D, it's a field of crosses, which is always going to have one vector or one line in the cross, which is perpendicular to the boundary. And so you see that in this case, everything is basically uniform, except for, so in this case you would expect that you have a degree 1/4, I think, vortex.
So what are you picturing here is the pair of P1 and P2. So here the picture.
So it is P1
and P2, but they minimize that.
It is a stationary point that we recover by through the gradient flow. Yeah. Okay. And so this is what you're going to do for free cross field. I mean, this is irrelevant. It's just some large Q, large tensor or matrix Q. This is not really going to convey any information to you. It's just that you're going to end up with some huge potential. The boundary conditions look like this. All of that doesn't really matter that much. This is a picture in 3D. So it's the same problem. So except now this is orthonormal frame. It's a critical point for orthonormal frames on a shell, on a spherical shell. And as you can see, so the colors here simply indicate the value of the nonlinear potential. As you can see, you end up with exactly 8 singular points, as you should, and they're equidistant. Now, this is a similar picture, except that a similar computation, except now it's not in on a spherical shell, but inside the ball. Same idea that the colors represent the deviation from, just represent the values of q squared minus q, where you see a red color, this thing is the largest. So in this case, you see that the gradient flow produces a bunch of line singularities connected at quadruple junctions. You still satisfy the correct boundary conditions in the sense that you still have 8 singularities on the surface of a sphere. Now, this configuration most likely is not energy minimizing. Because, let me see, so before this is a cross-section, by the way, of the same cross-section of this figure along the plane, one vertical plane. And so you see, again, this analogy with crystalline solid and 4 possible distributions. Now, why is this configuration not energy minimizing? Because in this case, actually, you can show that there are admissible fields. So if you want to build a competitor here, which has one vector on a boundary in the frame, which is perpendicular to the boundary, you should be able to do so with one point defect or of a degree higher than, I guess, a degree 2 in this case, which obviously is going to have lower energy than a competitor which has a bunch of line defects. Because this is something that was of interest to people who are doing meshing, this is, or maybe also veterinarians, I don't know. But this is one of the typical things that they consider, one of the typical domain types that you want to mesh. And so in this case, again, same conditions, that you have one vector which is perpendicular to the boundary, you end up with some fairly complicated structure of a singular set. Again, likely not energy minimizing, but stable. Right? So these are local minimizers of some sort. How much time do I have?
You have 20 minutes.
All right.
May you clarify? So when you go back to this previous slide, so are these red lines in the 3 line orthogonal line fields shown the same way, or they're just in one of the fields that you just right now visualize?
No, I'm not showing orthogonal lines here at all, right? So these are just singularities of that vector field, right? So
It's one field.
no, it's all, it's an entire frame, right?
Okay.
It's an entire orthonormal frame, but at these lines, on these lines, the frame is no longer defined.
So, Dmitry, by disclination, then here you mean discontinuity is in the rotation.
Yeah, because there is no, that's why I said disclination from the beginning. There are no rotations here. No translations, I mean translations, not rotations. It's all only rotations. Number one. Number two, also the what do you call it? The elastic energy is something which is totally made up.
It's on the second gradient.
Right. So this is some higher order terms. That, so for instance, I guess going back to Adriana's talk, here maybe you can impose some sort of a curl conditions on this. Say that you want to penalize a curl in some way. Maybe, there are some analogies, some better analogies with implications that one can okay, so then in the remaining time, we'll talk about other type of frames that we have considered. So our original idea was to look at different kinds of frames. So I already described orthonormal frames, meaning that in that case you want to fill the space with orthonormal lines. What I'm going to describe now is a different idea. So you want to file the space with not with 3 orthonormal lines, but with tetrahedral. It is possible that you want to do the same thing with icosahedra or some other situations, and what we wanted to do is to develop a sort of a uniform procedure which tells us I want to tile the space with a certain object, and I want to develop a Ginzburg-Landau-type theory for these objects. Can we develop somehow a uniform procedure which will apply to all of these cases? So far, the answer is not exactly. So some parts of it are somehow uniform, and some parts work in a different way. And I'm not going to go into the details of that. I just wanted to mention it. All right. So why would you want to tile the space with tetrahedra? So one possible description, one possible thing which might be of interest in material science. So in the previous case of orthonormal frames, you can think about cubic lattice, and you want to fill the domain with a cubic lattice. In this case, we can talk about a certain liquid crystal phase, novel liquid crystal phase that already has been mentioned at least once here, something called bend-core banana-shaped molecules. Unlike the standard nematics, which are just lines, these guys have shape like bananas. And so they have more complicated, for our purposes here, they just have more complicated symmetries than just lines. And in particular, molecules like that, so the issue that we discussed before, that, for example, for nematics, the probability of finding head or tail of a molecule pointing in a specific direction is exactly the same. For things like this, that might be violated. And so in that case, the first moment becomes relevant. First moment becomes relevant, maybe the second moment is still relevant. In fact, for these molecules, as I'll show in the next slide, if you want to describe all known possible phases of these materials, it's not enough to just look at the first moment or look at the second moment. You have to look at the first three moments. So both first moment, Q tensor, and also the third moment. So one possible way of looking at this is that if you have a probability distribution function, you can expand it in terms of moment. This is something called the Buckingham's formula. Details, again, do not really matter. And so then, up to the first three moments, F can be recovered in this form. First moment is a polarization vector, right? So in this case, it's not necessarily zero. We don't have this identification. I mean, it's more complicated than that, but we can just think about it in this way, that we don't have identification of head and tail. So P is not zero. Q is still the same as a standard Q tensor, and now we have also the third moment tau, which describes a tetrahedratic order, meaning that this is precisely what you want to consider in this case, that you are filling the space with tetrahedra, and that is described by the third moment tensor. All right, so I have just discussed the n-cross fields. Now we're talking about the k-frame fields. You are in Rn and you want to generate a frame of k vectors now. And what you want maybe all of these vectors have the same angle between them. And so for tetrahedra, for example, you have 4 vectors like that in 3D. Or in 2D, you can have 3 vectors at 120 degrees to each other, and because we're in Germany, I'm going to call this a Mercedes-Benz frame. So, either tile a 2-dimensional space with stars like this, or a 3-dimensional space with tetrahedra. Exactly the same sort of approach as I described before. Except that in this case, so now I'm stepping back from my interpretation of bent core liquid crystals. Forget about those. I'm simply concentrating on the third moments. And in this case, I'm simply trying to fill the space with tetrahedra. So if at every point in a space you have 4 vectors that end at the vertices of a tetrahedron, then the first moment that we can compute based on these 4 vectors, which is not trivial, is the third moment. You can show that the first moment and the second moment, I think first moment, one of them vanishes, one of them is a constant. So now it is a third order tensor. Before, 4 for the tensor was a matrix of matrices. This one is going to be a vector of 3 matrices. And one can show also that these matrices are all going to be traceless in this case. And so I'm going to work in a set of third order tensors in Rn, which are trace free. All right. So in this case, it turns out that, again, exactly the same condition as, well, not exactly the same, but a similar condition to what I described before, that Q satisfies a projection condition. It still works. I mean, it is a similar condition with some constant, but it still works in the same way. Q's again are symmetric with respect to all possible permutations and satisfy the trace condition. And so exactly the same question as before arises if I have third-order tensors that satisfy trace conditions that are symmetric and satisfy the nonlinear constraint. Am I able to recover the frame field, the tetrahedral out of this? And it turns out that the answer to this is yes. It's I'm not describing neither in this case nor in that nor here how exactly this is done. There is a lot of linear algebra that one is supposed to do here, but this is doable. And so we have a theorem which actually shows that this is indeed the case. And so then we can do a Ginzburg-Landau relaxation in exactly the same way as before, just penalizing variations of Q again in the most straightforward way. Of course, you don't have to do it like this. You can have something much more elaborate here, but it doesn't really matter to us now. And then we penalize a nonlinear constraint, and so then there is some large coefficient. So when epsilon goes to 0, you would expect that most of the time your Q is tetrahedral frame, except for some small region, region of a small measure, where you'll have singularities. Again, just like before, we can either prescribe the boundary constraint, or we can do a associated surface energy with this. And more pictures. So in this case, first I'm talking about this Mercedes-Benz MB frames. Again, same idea that I want the frame to have one vector on the boundary which is perpendicular to the boundary itself. So if the domain is a triangle, then of course, then there is no hole. Then simply a constant vector field is going to, constant frame field is going to be an energy minimizer. But if you have, if you drill the hole, then this hole no longer is going to, the frame field is no longer going to match with the boundary. Of course, we cannot really talk about winding on the boundary where boundary is not smooth, but on the smooth part of the boundary, then you must develop singularities. Again, the quantization here, the degree is quantized by 1/3. So if the winding is 1, then you have three defects. And these defects have a structure like this. Now, next, one thing which was a bit surprising to us, but nonetheless it's true, if you have these tetrahedral frames, so I'm only showing you 1/4 of a domain which is a disk. So in this case, domain is disk in R2. And the target set is a set of these tetrahedral frames. It's third-order tensors. You want the tensors to adhere to the boundary in the sense that, again, one of the vectors is normal to the boundary. Otherwise, the frame field on the boundary is free. And it turns out that in this case, also, it is possible, topologically possible, for the frame field to escape into the third dimension. For those who are familiar with the crystals, that is what happens there. That means that basically you can find a solution which has no singularities inside the domain. So even though the object somehow is more complicated than just a vector, you still have the escape. However, if you run a gradient flow starting from these boundary conditions that I'm not explaining, but these are boundary conditions which allow for escape, then it is also possible to get critical points, which are local minimizers, which do have singularities. This is again similar to what is known for liquid crystals in particular. I think Radu and Ardir have some results for liquid crystals which show the existence of local minimizers like this. How much time?
5 minutes.
5 minutes. So another thing which is sort of interesting here is that the fundamental group for this sort of symmetries is much more unusual than what we're used to for the regular Ginzburg-Landau. I don't have time to go into the details, but from simulations you can actually see how the winding works around, for example, in this case, 3 defects that you see. So you can actually observe that around each of these defects you wind exactly by rotating around one of the heights of the tetrahedron by 120 degrees. Another manifestation that this actually works as intended is this simulation, again, it's in 2D, and the boundary data is in a homotopy class where one of the vectors is supposed to rotate by pi over 2. Now, if you analyze the fundamental group in this case, then actually this configuration should have a higher energy than 2 homotopies where you rotate by 120 degrees or by 120, 60, 120. And that's actually what simulation shows, that if you start from something which has one defect with in this homotopy class, then it splits and it gives you the correct behavior. And the last thing, so remember the picture for orthonormal frames for the 4-Fodor tensors, where we developed a cage like this, which was in the form of sort of a cube. For tetrahedra, again, the cage develops, and again, this is not an energy minimizing configuration, but it is a stable configuration. In this case, Poincaré-Popov says that you have to have 6 defects on the boundary. Indeed, you do. And those defects end up connected by line defects. Again, this is not an energy minimizer because you have line defects. You can actually construct, again, competitors which only have one surface defects and no singularities in the interior. On the surface, the defect will have a higher degree. And you can analyze what happens to the frame field in the vicinity of each junction, because it was of interest to us what exactly happens on each junction. And you can see in this case, and again, I don't want to go into details, but you can see that around each arm of the junction, actually, your tetrahedron rotates by 120 degrees with respect to different axes. So that if you come from here and then you split, then the group element here is actually a product of group elements there. So it works as it should. Right.